All right, hello and welcome back. In this video, we're going to cover section 2.2, solving linear equations, part 2. So this is a continuation of our last video on solving linear equations in one variable. So here we'll cover solving equations containing variables on both sides of an equal sign. Then we'll look at solving equations containing fractions or decimals. So some techniques on how to do that, make them a bit easier to solve. We'll look at solving equations with no solution or an infinite number of solutions and when that would be the case. And then we'll be using what they're calling the 5 steps for solving applied problems. All right, let's get started. So, solving equations containing variables on both sides of the equal sign. In the last video, we were looking at equations that just had an x or a y on one side, but as you can see here, in this example, let me write it a bit bigger here, 3y minus 11 plus 7y equals 6y plus 9. So in this case, our variable is y, and we have 3 of them, and they're on both sides of the equal sign. And what is this question asking us to do? It's wanting us to solve. And remember, that means that we want to use some rules of algebra, move things around, combine like terms, and get to a point eventually where we just have a single, in this case y, single variable equals some number. So what should we do first? It might be kind of unclear, and it's not super necessary to do a particular thing. As long as we're following the rules, there's many paths that will lead us to the solution. So as long as we're doing the right kinds of moves, it doesn't necessarily matter where we start. The first thing I usually do is look for parentheses. Are there any parentheses to clear out? In this case, no. The next thing I think about is combining like terms. That would be my first step. So I want to combine like terms. So what would be like terms here? I see the 3y and the 7y. They both have a y attached, and it's both y to the first power. So I can combine those together. If you need to go off on the side, write things out. This one's pretty simple. 3y plus 7y, that would give us 10. We have 3 y's, we had 7 more. So those two will combine together to make 10y. We still have this minus 11, and it's still equal to 6y plus 9. Now we can make, we still have the y's on both sides of the equal sign. So we can make the kind of just aesthetic decision to move all the y's over to the left side or the right side. People typically like to move it over to the left, so I'm going to do that. And remember, in order to move across the equal sign, we want to use the opposite operation. So I have a positive 6y on the right side. So in order to move it over, I would subtract 6y from both sides. And it's going to subtract from that 10y. So on the right side, it'll cancel. And on the left side, 10y minus 6y, there would be 4 left over. So 4y. We still have the minus 11. And then on the right side, we have our positive 9. So now this is looking a bit like what we were looking at in our last video. So let's continue. Still trying to solve for y. I want to move this negative 11 over to the other side. So since it's negative, I will add plus 11 plus 11. Bring down my 4y. The 11s will cancel. So I'll bring down my equal sign. And then 9 plus 11 will give us 20. All right, we're almost there. We have our y on the left side, but it's being multiplied by this 4. So since it's being multiplied, I'll do the opposite operation and divide. Divide by 4, and we'll do that on both sides. So the 4s will cancel on the left side. So I'll just have y on the left side equals 20 divided by 4, and 20 divided by 4 is 5, positive 5. And we can check the solution if you'd like to. So basically, we just need to follow the process of cleaning things up, combining like terms, getting our variable over to one side of the equation, and solving it, just like we did in our last video. All right, let's make it a little bit more complicated. Look at our next example. So in this case, we have 9t plus 4 minus, and we have open parentheses, 7t minus 2, close parentheses, equals t plus 6 times t plus 1. All right, what a mess. There's lots of things going on, but I'm just going to follow that same process. It wants me to solve, so eventually I want to get a single t, everything combined, over to one side of the equal sign, and everything else over to the other side. And the first thing I want to do is clear out the parentheses. So if there's something in front of the parentheses, like on the left side I have this minus, on the right side I have the 6, you'll want to distribute these to everything inside. You want to distribute. And you can see this visually as, usually like to write little arrows. Let me make this look a little cleaner. So we would distribute to the 7t, distribute to the negative 2, and the 6 would distribute to both the t and the 1. So yeah, when there's a minus in front of a set of parentheses, think of it as like a minus 1, a negative 1 that's in front. So each item inside is going to be multiplied by negative 1, which will just flip the sign. If it's positive, it will become negative. If it's negative, it will become positive. So let's write out what this will produce. So I have my 9t plus 4. So the negative 1 will hit the 7t and make it negative 7t, or we could say minus 7t. And then the negative 1 will hit the negative 2. Negative times a negative is a positive. That'll make it a positive 2. Equals t plus, okay, the 6 will multiply with the t. 6 times t is just 6t. And then 6 times 1, it's a positive 6 times a positive 1. So the result is a positive 6. So notice I kind of did 2 steps in one with that one. As you get more comfortable with this kind of process, you'll be able to start combining more steps, but when you're first starting out, it might be beneficial just to do one thing at a time. Maybe just distribute the left side and then write that line out, and then on the next line, distribute the right side. that might help you keep a more clear mind. It's easy if you try to combine too many steps at once. It's easy to kind of lose track of what's happening. You might start to leave off some numbers, make little errors. So this kind of goes along the line of thinking of trying to be intentional and neat in our work. All right, so we got rid of the parentheses. Now we're kind of like where we were in the previous problem. We have, in this case, t is our variable. We have that one, and then there's 2 on the right side. So those are all going to be like terms. We're going to want to collect all of those together and get it on one side of the equation. So I want to combine the 9t. So we have like 9t minus 7t. And what else are like terms on the left side of the equation? We also have this 4 and this 2. You don't always have to write these arrows. I'm just doing this as a visual tool. But if it's helpful for you to write them out, definitely go for it. And then on the right side, what are like terms? I have this t and 6t. I have the positive 6, but there's not another number to combine it to. So let's combine like terms. So on the left side, 9t minus 7t and then 4 plus 2 will give us 6. Then we have our equal sign. On the right side, t plus 6t will give us 7t plus 6 on the right side. And it's already looking a lot better. Things are cleaned up. So we still have t's on both sides of the equation. Now I could move this 7t over to the left side. By subtracting, it'll give me a negative number. Maybe it's easier to move this 2t over to this side. And again, you're free to choose which side you want. And most people move things to the left side, but we want to try to make things as easy on ourselves as possible. So you'll pick up these little tricks as you get more practice. So I'm going to move the 2t to the right side. It's positive on the left side, so I'll subtract it, minus 2t, minus 2t. So on the left side, that cancels out. Just got this 6 left over here. Let's make it look a little bit nicer. On the right side, 7t minus 2t, 5t, plus 6. All right, looking pretty good. Now we want to keep this t here and move everything over to the left side. So I want this 6 to go and combine with that 6. And check out what's going to happen. I'll subtract 6 from both sides. Since it's positive here, there's an addition, so I'll do a subtraction. So, oh, I don't know why I'm writing 4. Minus 6, minus 6. So on the right side, this is going to cancel out. And then on the left side, it actually also cancels out. 6 minus 6 is 0. In this case, I'm going to write a 0 on the left side. So 0 equals 5t. What does this mean? It means there's some value of t that when I plug it in and multiply it by 5, the result is going to be 0. What number could that be? Well, we can find out just by continuing the math. We have 5 times t. There's a multiplication. So I'm going to cancel it out with a division. 5 divided by 5. And I'll divide by 5 on the left side. So we get our cancellation here. So this will solve it for us, equals t. And on the left side, 0 divided by 5. 0 divided by anything will just give us 0. Well, unless we're dividing 0 by 0, and that's a bit more tricky. So we'll save that for maybe a calculus class. But for now, we got 0 divided by 5. So 0 equals t, or if you prefer, you can say t equals 0. So 0 can be a solution. That means if we went back to our original problem and plugged in 0 for every t, we would solve our equation. We would make both sides equal to each other. All right, so that's really just an extension of what we did last time. We're just making it a little bit more complicated. All right, let's take a look at some strategies for solving equations that contain fractions or decimals. We did this a little bit last time, and we had to combine some fractions. There's some big set of rules on working with fractions, and that can be a little bit annoying. A lot of students are afraid of working with fractions, definitely want to get over that fear in terms of not knowing the rules. Best case scenario has become annoying. All right, but we can try some other processes too. So this is one procedure. They're saying eliminating fractions from an equation. We can eliminate them. And what does that mean? It says to eliminate fractions, determine the least common denominator for all of the fractions in the equation, then multiply both sides of the equation by the least common denominator. So let's look at our example and try to getting some weird headphone stuff going on. All right, hopefully everything's okay. So let me write this down. I have 1/2 times 3b plus 8 plus 3/4 equals negative 1/2. Lots of fractions, things would get complicated if we keep them around, but there's something that we can multiply by everything that will actually just clear out the fractions. And it's saying we want to use the least common denominator of all of the fractions. So what are our denominators? Our denominators are 2 and 4. The least common denominator is the smallest number, basically the smallest number that you can make all the denominators by multiplying by something. And it takes some practice to learn how to recognize this. Hold on, I think I'm still having some headphone issues. Let me do something. Definitely. Let's remove it from here. It's because I have my computer open as well, and my headphones are connecting both to my head and my computer. There's too much going on. So just like my brain, I need to remove distractions. All right, hopefully things will be good from here on out. So I have a 2 and a 4. What can I make them both by multiplying by something? Well, if I multiply the 2 times 2, I can make it a 4, and then they would be the same. So in this case, I would say 4 is my least common denominator. 4 is the smallest number that I can turn both of these denominators into. So it's saying to multiply both sides by this least common denominator. So let me write this out in another line just so we can visualize. I'll make a little bit more room. So I would want to multiply the entire left side. I'm going to put this in parentheses and say I'm going to multiply this entire expression by 4, which is my lead. The right side as well by this 4. All right, so this 4 is going to distribute to everything inside. Now this 1/2 times, open parentheses, 3b plus 8, because they're multiplied together, you can think of them as like a single object. So the 4 will only multiply by it one time. Like we're not going to distribute into the inner parentheses. That wouldn't be correct. It's just going to basically hit what's in front of the parentheses. So let me write it like this. What we have is, I'll draw my little arrows. So this is going to distribute here, and then it's going to distribute all the way over to the 3/4. And then on the right, the 4 will multiply by the negative 1/2. So I'll write it out first. So I got 4 times 1/2 times 3b plus 8. So you see here, this all just becomes one object of multiplication, plus 4 times 3/4, because that 4 came over, multiplied, equals 4 times negative 1/2. So I'm just multiplying everything by 4. And we can think of this as a 4/1. Think of this as a 4/1. Think of it as a 4/1. I'm writing that because I'm going to see how these fractions will reduce. So here, multiplying 4/1 times 1/2, the 2 goes into the 4 2 times. Or we can think of that as just 4 divided by 2. So this will reduce just to 2 times 3b plus 8. Here, we essentially have 4/4, so that cancels. So we'll be just left with that 3. And then over here, we have the same, 2 goes into 4 2 times. In this case, we have this negative, so don't want to forget about that. This will reduce to a negative 2. So notice now how all of the fractions have been eliminated. Now we don't have to worry about the fractions. Now we have like a problem like what we had before. So this 2 will distribute to both terms. So eight is 16. And then we still have the plus 3 equals negative 2. So we still have this 6b on the left side. So 6b, 16 plus 3 is 19, equals negative 2. Now let's move the 19 over to the other side. So I'll subtract 19 from both sides. So 19s will cancel. I've got 6b left over, and then negative 2 minus 19 is negative 21. Subtracting from a negative, the result is more negative. All right, let's bring this up here just to make a little more room. I've got 6b equals negative 21. Almost have it solved. I just want to divide both sides by 6. So cancel on the left side. I'll just get my b left over equals negative 21 over 6. So it looks like it's solved, but I always want to try to reduce my fraction. is there something I can divide both the numerator and the denominator by? In this case, I can divide 21 by 3. I can also divide 6 by 3. So I will get that b equals, it'll still be negative. 21 divided by 3 is 7. 6 divided by 3 is 2. And then I can ask myself, can that be reduced more? In this case, it cannot. So that will be my solution. All right, so that was a method of clearing out my fractions by multiplying by the least common denominator. So that was our strategy. So let's look at something similar for decimals. So this is eliminating decimals from an equation. So it says to eliminate decimals from an equation, multiply both sides of the equation by the smallest power of 10 that will eliminate all decimals from the problem. When they mean the smallest power of 10, that means a 10 with a certain number of zeros. What they're really doing is adding some exponents. 10 to the first power is 10. 10 to the second power is 100. Notice there's like 2 zeros here. 10 to the third power is 1,000. 3 zeros. So that's just what they're talking about, some power of 10. And you can know which one to choose by looking at how many decimal places you have. So let me first write out our question. We have 0.05a plus 0.2 times a plus 3 equals 0.1. So what should I multiply all of these by? Well, I want to find basically the largest number of decimal places. So I have 1, 2. I have 2 decimal places here. I have 1 decimal place here, and I have 1 decimal place here. So the largest number is 2. So that is 2 decimal places. So that means I would want to multiply everything by 100 because it has 2 zeros. That's essentially going to move the decimal over 2 places. If I have something like 0.05 times 100, it basically just moves this decimal place over. That would be multiplying by 10, multiplying by 100. It'll make it a 5. 0.05 times 100 will give you positive 5. All right, so let's write it out. I'm going to multiply everything by 100. Plus 100 times, we have 0.2 times a plus 3. And I'm going to multiply the right side also by 100. So when I multiply, we just said earlier, when I multiply 0.05 by 100, it's going to move the decimal place over 2 spaces. So that'll just make this 5a. Plus, now here, I'll just show this on the side. If I'm doing 100 times 0.2, it's going to move, looking at this 0.2, it's still going to move it over 2 spaces. So 1, 2. Notice there's like this empty space here, and you would just fill that in with a 0. So 0.2 times 100 will turn into 20. And we still have the a plus 3. And same deal here, we have 100 times 0.1. That's going to turn it into a 10. we have 0.1. Technically, there's like an infinite number of zeros behind this, 0.1000000 forever. So we're moving this over 2 spaces, 1, 2, we get 10, 10.0. So now here we've cleared out all of our decimals. We no longer have to think in decimal mind. We can just treat this like an equation. And even though it looks different from this one, because we multiplied everything by the same number, we just scaled it, it's still the same equation. So let's continue. We want to solve. So let's distribute the 20 to both terms in the parentheses. Let's clear those out. So now I have 5a plus 20 times a is just 20a. 20 times 3 is 60. This is equal to 10. Let's combine our like terms. On the left side, I have 5a plus 20a. So that will give us 25a plus 60 equals 10. Now I will subtract 60 from both sides. So it'll cancel on the left side. I'll just get my 25a. And then 10 minus 60. Starting with 10, imagine you have 10 bucks and you spend 60 bucks. How much would you be in debt? You would be $50 in debt. You can think about like subtracting 10 from 60 and then making the result negative. That's one trick you can do. All right, we're almost there. Just want to solve for a. It's being multiplied by 25, so let's divide by both sides. Divide by 25, divide by 25. Cancel on the left side. So I get a negative 50 divided by 25. 25 goes into 50 2 times. And we have the negative, so the result will be negative 2. And that will be our solution. All right, so kind of a similar process for each one. If we have fractions, you can multiply everything by the least common denominator and clear out the fractions. If we have decimals, we can multiply by some power of 10, a 1 with a certain number of zeros, and the number of zeros that you choose is based off of the largest number of decimals that you have. So pretty cool techniques to make things a bit easier to work with, because people tend to want to avoid working with the fractions or the decimals. You could just leave them and solve it like that, but this is a way of making it a little bit easier. All right, now let's look at solving equations with no solution or an infinite number of solutions and when this would occur. These are two different scenarios. So let's look at this little summary box. It says there are 3 possible outcomes when solving a linear equation. So far we've had a solution for everything that we've worked with. But it's possible that, and so far we've had, so far we have had a solution with every equation that we've worked with. And we've had a single solution each time. So that's our first case. We could have one solution. And it says the solution set is some real number. It says an equation that is true for some values and not for others is called a conditional equation. It's conditionally true. There's only one number you can plug in. Like in our previous stuff, this is saying that our single solution is negative 2. -2 is the only number that if we plug it in to our original equation, it will produce a true statement. So that's when you have a single solution. Now it's possible to have no solution. I mean, all of these previous equations we've worked with have been designed to have a solution, but you could come up with something that just doesn't make sense, that doesn't have a solution. It says, in this case, the variable will drop out and there will be a false statement, such as -9 equals 2. And we'll see an example of that. In this case, they say the solution set is this symbol. It's a 0 with a line going through. This is the empty set. It's mathematical notation essentially for nothing. Another way you could express this is just some brackets with nothing inside. It's the void, nothingness. It says an equation that has no solution is called a contradiction, meaning it's a false statement. It doesn't work out. It's not true. So that's our second case. Our third case is having an infinite number of solutions. It says, in this case, the variable will drop out, and there will be a true statement such as 15 equals 15. Something equals itself. In this case, the solution is anything. You could plug any real number into it, and that's what they say here. The solution set is all real numbers. The set of all real numbers there's a mathematical symbol. We can say this. It looks like an R with 2 lines attached to it. So this is just some notation. Notation for saying nothing, and notation for saying everything. Not technically everything. This is just saying all real numbers. But more on that later. Let's see some examples and it'll make some more sense. All right, starting here. We have 11w minus 9 equals 5w plus 2 times 3w plus 1. Can we tell? Will it have a solution? Will it have no solution? Is every number a solution? It's not exactly certain. It's hard to tell. So let's solve it and see what we get. First thing I want to do is clear out the parentheses. So I'll distribute the 2 to both terms. Let me rewrite the left side. 11w minus 9 equals 5w. 2 times 3w is 6w. 2 times 1 is 2. Now let's combine like terms. I'm going to start writing a little bit less. Hopefully you've picked up on this process. 11w minus 9. We have 5w plus 6w is 11w plus 2. Now I want to get all my w's on one side, and check this out. We have 11w on the left side and 11w on the right side. It's the same thing on both sides. Now what's going to happen if I subtract 11w from both sides? If I'm saying like I want to move this 11w over to the other side, I would subtract it from both sides. It'll clear out on the right side, but 11w minus 11w will also cancel on the left side. So my w's are canceling. I'll be left with -9 on the left side equals +2 on the right side. This is a contradiction. -9 is not equal to +2. Doesn't make sense. So this is the case. This is like our number 2 up there. This is the case where there's no solution. So I'd say no solution, or we can use our symbol, the empty set. Mathematicians like to write as little as possible. So instead of writing no solution, we use this symbol as a single symbol. This also allows us to sort of transcend the English language. If you write no solution, somebody that speaks French or Mandarin may not understand. But if they've studied mathematics and you throw them this symbol, they'll know exactly what you mean. They'll know, oh, no solution in whatever their native language is. So mathematics has a way of transcending local language. That's part of what I think is so cool about it, about seeing mathematics as its own language. But that's just a side note. So no solution. So what happened here? We tried to solve our equation and we arrived at a contradiction. So we got to throw it out. Math is a language where we want to only have true statements. We want to only speak the truth. So what does this mean if no solution? It means that there's no value of x that will ever make this, or in this case w, there's no value of w that will ever make that statement true. You can try plugging in any particular real number and it will never produce a true statement. Let's look at another example. So this wants us to solve 10r minus 3r plus 15 equals 7r plus 15. What will we have? One solution, no solution, every possible solution. Let's find out. Just go about solving it normally. Got some like terms on the left side. 10r minus 3r is 7r. 10 minus 3 is 7, plus 15 equals 7r plus 15. We have the same thing on both sides. We could continue solving this. We could subtract 7r from both sides. That'll give us 15 equals 15. Definitely true. This is a true statement. So we had the same phenomenon where our variables canceled. It canceled on both sides. But last time we got an untrue statement. Last time we were saying negative 9 equals 2. Not true. That's a contradiction. In this case, this is true. 15 does equal itself. So this means we have an infinite number of solutions. So they used this. They said the set containing, and they wrote it out, all real numbers. But let's escape the English. We'll just say our symbol. All real numbers. Anyone that studies math will see that and know what you're talking about. Pretty cool. Oops. So what does this mean? It means that you could plug anything into this equation. We could plug in 2 for r, and we would get a true statement. We can plug in 5/3, and we would get a true statement. We could plug in 60 billion point 2, and we would get a true statement. Anything that we plug in will be true. Interesting. So these are our two special cases. Either our variables cancel out and we get a contradiction. In this case, we have no solution. Or our variables cancel out and we get a true statement. We call that an identity. And in that case, the solution is all real numbers. All right, our last step, we're calling this using the 5 steps for solving applied problems. So applied problems give some real world context. So let's see what they say. They say, step 1, read the problem carefully, more than once if necessary. It's good advice. Until you understand it. Draw a picture if applicable. That's extremely helpful. There's many times when I'm reading and sort of applied question, don't really know what's going on, and if I try to draw it out, make a little sketch, it can be helpful. Identify what you're being asked to find. Step 2, it says to choose a variable to represent an unknown quantity. If there's any unknowns, define it in terms of the variable. Basically say what your variable is equal to. What does X represent? Step 3 says to translate the problem from English into an equation using the chosen variable. So we'll see some examples of that. And then you solve and check the answer. Let's see some examples. So our first one says to write the following statement as an equation and then find the number. So what is our statement? 9 more than twice a number is 15. Find the number. It's kind of an odd statement, and it's kind of hard to see, like, what is it talking about? 9 more. It means like we're going to add 9 to something. 9 more than twice a number. Notice the vagueness here, a number, some unknown. The unknown is typically going to be our variable, x. So twice a number, twice this number, well, that would just be 2 times this number, twice some number. So we have our 9 more, that means we're going to add. A lot of times it's kind of backwards, and I don't know if this is a result of the English language or not, but they kind of put things sort of in reverse. We'll see this in subtraction as well. 9 more than twice a number, so we can think of that as 2x plus 9, is 15. Is, if you see that in a sentence, it's like saying it's equal to. This is, it's equal to 15. So let's write this a little bit nicer. So twice a number would be 2x. 9 more than that, we would just add 9. So here's our 9 more than twice a number is 15. Find the number. Well, that's just saying to solve this equation. So we've translated from this statement into something that we can solve. That's part of the power of mathematics. So let's solve it. We've been solving equations. Let's use our processes. I want to solve for this x. Let's move the 9 over to the other side. So we have 2x, 9's cancel out on this side, equals 15 minus 9 is positive 6. Let's solve for x. It's being multiplied by 2, so we'll divide both sides by 2. Divide by 2, divided by 2. That'll cancel on the left side. And then 6 divided by 2 is 3. That's the number that they're looking for. And this is kind of a strange example, but this is part of what we use mathematics for. We have some kind of complicated problem. And maybe it's not a word problem like this, but maybe it's a problem in physics, or it's a problem in engineering, or it's a problem in finance, a problem in budgeting. And we need to understand it. We need to solve it. We need to find a solution. Well, we can convert it into a mathematical problem and then use math to solve it. All right, let's look at another example. This one says, what is 2 less than 7? What? Well, that's our unknown, so that's like our x. Is our equal sign. Some unknown is, and this is what I meant earlier by like a lot of times it seems like it's backwards. 2 less than 7. 2 less than 7. 2 less means we're going to subtract 2 from 7. 7 minus 2. So we're saying x is 7 minus 2. What is 2 less than 7? Well, that's 5. It's a pretty simple example, but I think they showed us because of the little trickiness of that 2 less than 7. Let's look at our last example. Right, the following statement is an equation and find the number. So 5 less than 3 times a number, it's one expression, is, or we can say is the same as, that would be like our equal sign. The number, so that's our unknown, increased by 7. So let's translate this. Let's look at this first one. 5 less than 3 times a number. 5 less means we would subtract 5. Then 3 times a number, we can write that as 3 times x. X is what we're calling a number. That's our unknown. That's what we're looking for. So 5 less than 3 times a number is the same as, so is equal to, the number increased by 7. We would add 7 to that number. 5 less than 3 times a number is the same as the number increased by 7. It's kind of an odd practice, but when you work on word problems, this is an important step, sort of translating the word problem into some equation that we can then solve. So let's solve it. We have x's on both sides. Let's move this x over by subtracting from both sides. 3x minus 1x is 2x. We'll have this minus 5. The x's cancel on the right side, and we have our positive 7. I'll just write it as 7. So 2x minus 5 is equal to 7. Let's move the minus 5 over by adding to both sides, plus 5 plus 5. So we have 2x on the left side, and 7 plus 5 is 12. Almost there. Let's divide both sides by 2. So we have x, 12 divided by 2 is 6. 6 is that number that they're talking about. 6 is the number that they're looking for. All right, so that concludes section 2.2. This was solving linear equations, part 2.